rephrase that. All right, there'll be a quiz on Friday. I'm so sorry if that corrects itself. I want to tell you what I want to do today. I'm gonna mention we've mentioned 3-port. I gave you homework. If you have any questions about the homework, I'd like to do it. I'm going to do 1 2-port problem that we haven't done that can be a bit confusing because we haven't really done anything where there's an odd thing. We haven't done anything, at least I didn't do it on the board, where we had capacitors and inductors. But I'm going to do one particularly odd problem. So first, before I just take off the lecture, anything about the homework at all? Yeah.
This is about the homework, but have you graded the ABET projects yet?
All right, I'll level with you. Those ABIT projects are with another professor right now, and I'm waiting to get them back before I can say anything about them. And you have to understand, I have no control over people above me, so I can complain or remind or whatever. But I'll tell you what, I'll make a deal with you. Now, somebody wanted their grades. Was it you, Carmen? Did you say?
Yes.
Yeah, I will send people their grades. I was kind of holding out for that.
Okay.
But I'll send you all your grades. I'll just take it because they're an Excel spreadsheet. I'll cut and paste and just send it to you. I know I can put them all up on Canvas. I prefer not to do that for other reasons. I've had problems with Canvas. I don't know if you all have problems, but every once in a while, Canvas just does stuff that's bizarre. I mean, you'll lose data sheets. Well, I should say you'll lose. They'll be unavailable for a time. They're never really long. Okay, now, homework problems. You had S parameter problems, right?
Yes.
Did you all try at least? Acquaint yourself with anyone? Any questions at all? If you didn't have questions, it's fantastic. But if you do, now you'll notice if you had the reading, Dr. Wentworth's book talks about lossless systems, and he also talks about reciprocal networks. Those are two things. There's the real reason I don't even bother with losses. If you look at a network, any network, and it's got a resistor in there, it's lossy. It's a no-brainer. You understand that, everyone in class? If it has a resistor, it is lossy. If it has just inductors and capacitors, it is lossless. Now, if you go to measure the network, real networks, 8 S parameters, there's always some finite loss. It's impossible not to have it. It may be low, but there's always finite loss. So the mathematical formula, thank you, for the mathematical way to determine loss is take the S parameters and multiply them by their conjugate. You don't need to write this down, I'm just telling you. In Wentworth's book, he's going to show you this. I'm going to mention this to make sure at least if you hear this from somebody, you won't say, I've never heard that before. It'll be something that should jog your memory. Because there's certain things in this book that, yeah, they've got mathematical merit, but the actual, this is equation 1026. And so if you have any S parameter network, doesn't matter what it is. So you've got an S parameter network and you want to see if it's lossy. Well, if you take the transpose of that network times the conjugate of the network, all right? So this is a multiple. And if it's what's called the unitary, or I think he terms it unitary matrix. I'll show you what it means. It's simple. This proves lossless. So a lossless network has this. It'll be 1, 1, 1, and so forth. Basically, all ones in the diagonal and zeros here. Now that's called a unitary matrix, if it's a 3x3. If it's a 2x2, it would just be S transpose S conjugate would just be 1, 1, 0, 0. He calls this the unitary matrix. It just means diagonal terms are 1. That's to determine if it's lossless after measurements. He shows this in equation 1027. To me, it's a waste of time to do this. Any real network that you measure is going to have some measurable loss. So it's going to have some loss. How much loss really has to do with the internals of what you selected for it. Anytime you see resistors, it's lossy. You lose power, guaranteed. Anytime you have just capacitors and inductors, it's lossless. That's sort of the no-brainer approach that I use. And when you have amplifiers, there's always going to be some marginal loss based on resistance But you can have a gain too, because an amplifier amplifies the signal. And that's, so I'm doing my best to tell you the practical things you have to be aware of. This is just something that's mathematically kind of interesting, but it's of no real value. Another thing he talks about is reciprocal networks. You know, can anybody guess what a reciprocal network is, just based on what we're talking about? We've looked at them, but it's, I didn't use that word, maybe I did.
It's symmetric.
Any symmetric matrix where S11 is S22, S12 is S21 is reciprocal. Now the easiest way to determine that with your eyes is just look. If it looks the same from one port as the other. Y'all follow me on that? You don't need to do what he shows there. He takes S times S transpose to get that. You don't need to do that. Everybody with me? We can go through this, but it does no real. Engineers aren't worried about elegant math, they're worried about developing things and applications and designing things. So this is just something, I guess, in a sense, you should be aware of. Maybe you can find a use for it when you do analysis, but I don't use that. And I don't think anybody I know really uses that. So that's two things I want to do. I'll get to the 4-port devices. I didn't mention return loss and insertion loss right here. We did, y'all remember when we did filters? I talked about the actual insertion loss and the return loss. Do you remember this at all, class? How many do? How many remember loss, at least the term loss? You remember loss was in dB? All right. So anytime you talk about loss, and I'm going to just show you this right here, and this you will be quizzed on. Hint. This you will be quizzed on. All right? I can give so much away, but if you don't get it by now, I mean. So, here we're going to have loss in general. Loss is always in decibels. And so when we have any type of a port, we talk about loss, where you have, port 1, then you have some device, some S parameter matrix here, and here's port 2. You've got some incoming signal, V1 plus, some outgoing signal, V1 minus, some incoming signal, V2 plus, some out possible, and V2 minus is the way the ports usually designate the flow of, or really the signal coming in and out of the port. And when we talk about insertion loss, they just designate IL, insertion loss, IL, the abbreviation. And then it's 20 times the log of the magnitude of the reflection coefficient at port 1 or port 2, depending on. And the way Whitworth does this, he likes to do it this way, and this is common. I'm just going to say this would be the insertion loss of port I. So there would be insertion loss for both the port 1 and port 2. It's just the reflection coefficient. When you take 20 times, it's a minus, yes. In his book, it's a minus. All right, I'm going to say this. Insertion loss is always negative. It's always positive, but if you don't put the negative sign in front of there because the value is less than 1, then you get a negative number and it means amplification, and that's not the case. Insertion loss, they put minus 20 times the log of the magnitude, and this is real important. It's the magnitude, the reflection coefficient, so hear me now once, so you don't make the common mistake. If I took 20 times the log of A plus JB, y'all hear me on that? It's an imaginary number, or some magnitude at an angle, then you're going to get an imaginary and a real term here for insertion loss. Insertion loss is always just a real number. You follow me on that, anyone? So don't make that common mistake that I do see on tests, especially for kids that cram. They don't come to class, then they come to a final or something like this, and they got that insertion loss burned in their brain or somewhere, and they never realize it has to be a strict real, so that absolute value becomes critical. Got me on that? All right. That's insertion loss for either port. We'll do this simply for a simple one. Then there's return loss. Yeah. Then there's what's called return loss, and I'll put it over here. RL. Again, it's going to be minus 20 times the log. And the return loss, you know what? I'm so sorry about this. I did this wrong. This is actually return loss. My bad. It's embarrassing. And the reason is it's because it has to do with reflection coefficient. Normally what I do when I look at this stuff, when they put any kind of a loss, you will see something that indicates the reflection coefficient there. It's just 20 times the log of the magnitude of the reflection coefficient with a minus sign. I know that has to do with the return loss or the reflected loss, is another word for it. The insertion loss, which I'll show you here, this is my bad. That's minus 20 times the log. And what will happen with insertion loss, there will always be a sub something here. Like 2,1 would be minus 20 times the log of the magnitude of S21. Now, what it means, it will be either 1,2 or 2,1 for a 2-port. Never 2,2 or 1,1, because that would be return loss. But don't get hung up about that. All right, you'll be able to tell by the way the terminology is used. And sometimes they'll be talking about reflection loss, not return loss, and they'll be talking about what would be called the gain, forward gain in dB. All right. Now gain, y'all realize when we use just resistors, we can't have an amplification of power. Y'all follow me on that? You can actually get an amplification of signal if you're clever with the way you do it transmission-wise, but you can't amplify the total power. If you have a real amplifier, then you can amplify power, voltage, and current, all right? And then when they talk about gain in dB for amplifiers, that is an increase, and that negative sign won't be there. All right, just remember that. So this is the insertion loss for the, here it would be a forward gain, from port 1 to port 2, what's coming out, and the reverse gain, IL12 would be minus 20 times the log of the magnitude of S12. Here, and that's the way it is for 2-port parameters. I want to caution you about this, because this is a mistake people make in the real world. I mean, good engineers that have not been shown this. So all these port parameters, we're dealing with S parameters. Right? Now, this, I'm telling you, happens. When you work with a lot of stuff in the microwave, you'll see the S parameters given for devices, and they might even have mathematical functions or downloadable curves. So you'll have the S parameters versus frequency for all of them. I mean, for your device. And what you'll see is this. If this is some port 1, and they're going to have a signals coming in here, and then they're going to have something where they do filtering or amplification. Call this S1. So that's port 1. S1 here. Then coming out of this, now they may have a splitter here, but I'm not even going to insert the splitter. They're going to have something in here where they have another set of S parameters, S2. So this would be port 2. And this would be port 3. And what I have seen people do, and this is a mistake, is they'll say, I'll just take S1 times S2 to get the port parameters of 1 and call this 2. Do y'all hear me? You can't do that. It's called chaining. Have you heard the term chaining? Chaining things is like if you have input-output characteristics of H. Remember you had, it's called the transfer function. Because you had only one, your port, it was always whatever is coming in the first port, whatever voltage was developed, you could get the secondary voltage by multiplying it by the transfer function, right? So when you had just H parameters, you could say, if this is the flow of the signal, say this is V1, and you had an H parameter, H1, then V2 here would be H1 times V1. That's the flow, block diagram flow. You saw this in signals and systems, right? Then if I put another thing here, H2, I could say this voltage was simply equal to, call it V out, H1 times H2 times V1, and that's legitimate. You'll notice signal flow is one way, right? You can't do that with this. Think about the way S parameters are structured. On port 1, it's V1 plus V1 minus. Y'all follow me? Coming out is V2 plus V2 minus, right? If you take those and multiply, just multiply them, you get something wrong. You have to use what are called A, B, C, D parameters. How many have heard of these? All right. Where did you hear them, by the way? I'm just curious. What class? So, do you remember?
Now I'm not confident in my answer because no one else.
Does anybody else, do you remember H parameters for transistors? Forward gain, HFE? Do you remember GM, transconductance?
Analog and Digitron?
I don't know where you're going to get some of this terminology, but you will hear at some point about the different parameters. You'll hear about H parameter model for transistors, usually bipolar. There's HFE, the forward gain. There's the reverse gain. Y'all remember that stuff? Then there was S parameters that you heard about in signals and systems in here. And then there will be the transconductance, the G parameters that you get. You remember GM? All right, you've heard that? You'll hear about something called Z parameters for a network, but I'm not going to spend any time on that. They're impedance related, where it's a ratio of V to I in the ports. But then you're going to hear about A, B, C, D parameters. You can look it up. Now, when you take these S parameters and you turn them into A, B, C, D parameters, then you can chain things. And the reason is this, that what you'll have is, I'm trying to do this off the cuff. For A, B, C, D parameters, they take the S parameters, and for port 1, V1 in, it will always be in terms of voltage in, voltage out. So it'll be V1 in, V2 in, V1 out, V2 out, and you can do it with ABC parameters, but I don't think he mentions this in his book. Just hear me now. This, you can't say that these two right here can be given as S1 times S2. This does not work. Just remember this in the future. And I know this from experience because we did a project years ago at NASA where we had to extract what materials were involved in a 3-layer filter and waveguides. And what we had to do is find the parameters of the first layers to the second layers. And to do that, what we ended up doing is turning everything into A, B, C, D parameters so it could chain things. Hold on. I just want to see if he has it here. I don't think he does. I was going to give you a more formal example of that, but since you want to test it. No, you just have scattering. I'll put that up in the on OneNote just for your benefit. Anyway, don't do that. Okay. And you'll find out the matrix stuff doesn't work on that. So now, next thing I want to do is an example of a more difficult example with S parameters. And it's something here we're going to have an unmatched system where we need to get the S parameters. For this example, this is example 10.4, and it's in your book. All right, I'm going to show you exactly what I mean when I do this. I'm not going to do it the way he does it with just generalities. Suppose I give you an S-parameter matrix that looks like this. 1/2, 3/4, 1/2, actually, and 1, make that 1/4, 1/2 here. So that's my S-parameter matrix, given. I'm not putting any complex numbers in here. I'm not going to put magnitude in there. I have that, and I do this. Okay, I'm going to first make the short right at port 2. I was going to do this in a second so you can see the difference. So I'm going to shorten that out. And what I'm looking for is just the reflection coefficient right there, port 1. Now y'all follow me. I've given you the S parameters if it was matched. Now what I've done is shorted that port 2 out. You all with me on this? So I'm asking for the reflection coefficient. This is a problem. If I don't go through one of these, when I give it to you, people will be really, they'll be, because I'm assuming some of you didn't read this stuff and do the homework. This is a typical kind of problem that causes students concern. So we start by always writing the matrix equations. And y'all with me? I'm just stating what we have to know to get through this. Now, the next step is I'm going to replace the coefficients there with the values I put on the table there. And I just created those out of my head. So when I look at this, V1 minus is equal to S11, which is, can you figure it out? S11, if this is S parameters, can you, where's S11, guys?
1/2.
Yeah, it's this one, right? 1/2 times V1 plus S12,
1/2.
right? Right. And then V2 minus is equal to, can y'all see it? First, it's this, right, times 1/2, right? So it's 1/4 plus 3/4 V2 plus. Agreed, everyone? I'm just populating that with the matrix I gave you. I'm showing you exactly what you would be expected to know how to do. Now, after that, I shorted this, right? What does that mean to you mathematically? Just think about it for a second. What does a short do? Well, yes, you are right, but something a little different. Isn't that V2 minus plus V2 plus equals 0 actually? the wave coming out is equal to an opposite polarity of the wave going in. Y'all follow me? Now, I'm going to extend that in a second, but I want you to see this. First, you all agree with that? All right, very important. So, I can tell you what I'm up to. I want the reflection coefficient for that network, which is defined as V1 minus over V1 plus, right? That's what I'm after. So how do I get it? Well, I know that I'm going to use this to uncouple some of this, right? Now just watch this and see if you can figure it out. I look up here and I've got V1 plus down here, which I would like, in terms of V2 minus and V2 plus. Y'all follow me? And then I got V2 plus up there. Y'all with me on this? All right, now follow me. If this is equal to 0, V2 minus is equal to minus V2 plus. Do you agree with me there? Minus V2 plus. So V2 minus is minus V2 plus. Just doing this the way I'm just trying to show you as easy as possible what I'm up to. You know where I'm going with this. I want what? V2 plus in terms of V1 plus, so I can replace it in the first equation right there. Then I would have everything in terms of V1 plus, and I can divide V1 minus by V1 plus, and I can get this. Can you all follow my logic on this? All right, now keep going on this. What's my next step? Well, how about if I take this over here? Are you with me? I'm just going to do it right here. So if I take 3/4 over here, it would be minus 3/4, and it would be V2 plus would be equal to V1 plus, right? Right there, grab the cord. Y'all with me? Keep doing the math on this one. What does this become?
Minus 3 V2 plus.
Well, how about, so you want to multiply by what, 4 right off the bat? What he's doing is multiplying by 4 right here, and that gives,
That'd be minus 4. Yeah.
and that would be V1 plus. Do you all agree with me? Y'all see what's up? Now I've got V2 plus in terms of V1 plus, and therefore minus 7 V2 plus is equal to V1 plus. Agreed, class? I promise you, when I give this problem on tests or on quizzes or finals, there are people that absolutely drop the ball. They don't know what's going on. But y'all understand what I'm up to. I come over here now, to this equation, and I see V2 plus, and I'm going to rewrite that. So I have V1 minus is equal to 1/2 V1 plus 1/2. It's V2 plus. Well, V2 plus would actually be what? Minus 1/7, right? V1 plus. You agree with me? So it's going to be minus 1/7 V1 plus. Take a good look. I know this gets people every time I do it. Remember, we started with the measured S parameters for a matched system. Then we shorted the output, and we're deriving the resultant reflection coefficient. Agreed, class? Just take a good look and force yourself to think about this, because people will blow this, I promise you. Yeah?
So where did that 1/7 come from?
Well, remember, we originally had what? We had 3/4 and 1 as the coefficients here, and we had 1/4 here, right? So he suggested, and he's right, multiply everything by 4, and you get rid of the 1/4 business, right? So that made it minus 3, minus 4, and 1 is the coefficient. And I combined it to minus 3 and 4 to minus 7. Can you see this okay?
Yeah.
And so that was minus 7 right there in front of V2 equals V1, and therefore V2 plus is minus 1/7 V1 plus. Y'all with me? Try to focus. I know it's easy not. So now what happens Well, you all see here, I have 1/2, and then 1/2 minus 1/7, or really I have 1/2, and then I have, what, 1 minus 1/7 times V1 plus is equal to V1 minus, or V1 minus over V1 plus equal to the reflection coefficient at port 1 is going to be 1/2 times, and this is going to be 6/7, right? And that would be equal to 3/7 would be the value. Now, do y'all follow me the way I did it? And I chose real numbers. In his book, he has arbitrary numbers. You good with that or not? Yeah.
So could you just leave V1 minus in terms of V2? Just substitute.
Well, remember the definition of reflection coefficient is V1 minus in terms of V1 plus, right? The ratio. So you have to have everything in terms of either V1 minus or V1 plus. Did anybody look at that problem? No? You can see the tricks, and you can see how you can fall on your face on this. So that's the reflection coefficient when I take known port parameters and I short it. Right? Now here's something to think about for Friday. I'm going to erase this. I'm going to show you something where I'm going to extend this. Everybody with me on that? I'm going to lengthen that. Here is where it gets interesting, because people, you have to be able to rationally think through these and not panic. All right. So the next thing I'm going to do, I'm going to create another set of S parameters. I don't want to use the same one. To make this 1/4, 1/2, 3/4, and 1/2. That's my S parameter matrix. That's something you'll get like that. It could be a 3/4, probably a 2. Now I'm going to do this. Port 1, S parameter matrix. Or 2, short circuit here. It doesn't have to be a short. It could be a resistance, and I could put impedances in it. But here it's going to be a short. And the length of this is going to be lambda over 4. Are you with me? This is a little tricky. Now obviously you know the real crux of the problem is getting V2 minus and V2 plus right? So again, I'll remind you, here, that's V2 plus, and that's V2 minus. Make sure you agree with me on this. Remember, these are transmission lines, so it's plus, minus things, or waveguides where the waves are propagated. You got me on this, everyone? So now, I'm going to ask you right here, if you have a short circuit, what happens, regardless of the characteristic impedance, what is the reflection coefficient at a short circuit? In other words,
Is it
if you
1?
had a coax line and it was into a short, and I wanted the reflection coefficient at that point, what is it?
1?
Right here, call it the load. Well, almost. At the load, remember, reflection coefficient is always the impedance you're going into. Call that Z0. Well, that's a short, it's 0, right, class? Please, just listen. This is a port, that's the load, wave coming in, it's coming from a characteristic impedance Z0. It's going into a short, that has an impedance of 0, doesn't it, class? So if I take a look at this, it's 0 minus Z0 over 0 plus Z0, or minus 1. Now reflection coefficient is the ratio of 1. V1 minus over V1 plus, if this is port 1. Do you all agree with me? How many understand this? I'm trying to do this in a way that's as easy to understand as possible, with not skipping over things. Okay, now look here. Here I am at port 2, right? All right, think about it. The wave I got coming out is V2 minus, right? Please watch this and don't miss this, right? I got a wave V2 minus coming out. I track it, before it hits here, it's V2 minus and it's a phase shift, right? A phase shift of lambda over 4, or lambda over 4 is what? It's 90 degrees, isn't it, class? So, right before it hits right there, it would be V2 minus, and then it would be e to the minus j. I'm going to use 90 degrees here. So it would be a 90 degrees phase shift. That's still V2 minus is just the value of the wave. Sorry if it's a little, I'm not trying to be messy here, but I'm trying to make sure you see it. Maybe I'll put this up higher so you can see it. Probably better. So right before V2 minus hits, right there, I have V2 minus e to the minus j, 90 degrees. I said it was going to be 90, right? Now, it hits before it starts reflecting back, right? It hits, so we multiply it by the reflection coefficient. Do y'all follow me? The reflection coefficient is -1, right? So then I take minus that. This is the wave coming back, right? And the wave that actually hits here, which is V2 plus, is this wave shifted by another 90 degrees. Isn't it, class? I'm going to take you through it again. So I'd take this, and I'd multiply it by another 90 degree phase shift. And that would be V2 plus. Now let me take you through the steps again. Make sure you see this. Because here I use the short because the reflection coefficient is obvious. And it's easy to create this. So I'm coming out of port 1. Think about, I sent a signal in port 1. This is coming out of port 2. It goes exactly a quarter wavelength, so it's got a phase shift of 90 degrees. That's e to the minus j90. You all agree with that? Now it hits this, and so therefore I have to multiply it by the reflection coefficient, which is -1, correct? Then that goes another quarter wavelength. So this would be V2 plus. Do y'all follow me? This is the way you track these things. Now, something I'm going to say here, please just listen. You see how these exponentials can be added, right? So now I have minus V2 minus times e to the minus j 180 degrees is equal to V2 plus, right? All right, anybody else want to make a comment because you're about to see something? What's another way to represent e to the minus j 180 or e to the plus j 180? Anybody? It's like e to the minus pi radians, e to the plus j pi radians. Anyone? -1, isn't it? How many know that's -1? You're going to need to know this, right? It's -1. So if that's -1 times minus, I can get rid of it entirely, right? And that means V2 minus is V2 plus. Y'all follow me on this one. Now, you have the relationship between V2 minus and V2 plus. These are the S parameters. See if you can work with me on this one and give me the reflection coefficient at port 1 now. And then I'd be asking for the return loss. So just work with me. Make sure you get this. So when I do that, what would the reflection coefficient by definition be? Regardless of terminations, what is the definition of reflection coefficient from any port?
V1 minus.
The output divided by the input
Yeah.
signal, right? So that's just V1 minus over V1 plus, correct? Now we write the equations, the S parameter equations, and put in the parameters I gave. And then we go through that same process I did a second ago. So now I know V1 minus is equal to what? I'm not even going to put down S11. What is S11 by looking? Class? Anyone?
1/4.
How many see it's 1/4? Can you all follow me on this? All right. That's always the 1-1. This is always the 1-2. This is the 2-1. This is the 2-2. Please make sure you know how to read a matrix like this. It's an assumed thing, but I've learned from experience not all people know it. So it's going to be S11 or 1/4 right? V1 plus, what's, class?
3/4.
Plus 3/4 V2 plus, and then what's V2 minus? Can you read? Can you all see that or not? Isn't it 1/2 V1 plus? And what's next?
1/2 V2 plus.
All right, there, we wrote the two equations down. What's next?
Solve for one of the variables.
All right, what do we replace? Right here, right? And so I'm going to go to the second equation, and I know that V2 minus is equal to V2 plus, right? Y'all follow me? I made that determination. So I'm just going to make that a plus, if you don't mind. Clear? I see I need a V2 plus up here. I know I'm going to have to replace that with whatever this results in. So what's my next step anyway?
Get V2 by itself.
Yeah, and how do I do that?
Add or subtract.
How about we simply take this to the other side, right? Add minus 1/2 V2 to both sides. That makes this 1/2 V2 plus is equal to 1/2 V1 plus. Does it not, class? Y'all agree with that? Or what else could I say? I think you see it. Get rid of this, right? V2 plus is V1 plus, right? Please watch, right? So I'm going to just make this V1 if you don't mind, V1 plus. Do you all agree? V2 plus is V1 plus. And so if this is V1 plus, what do you see happening for the reflection coefficient? Well, what happens? I got V1 minus, I divide both sides by V1 plus, or I get 1/4 plus 3/4 or 1. Do y'all see that? You understand how I did that? Now here's the problem people will get. So far I did the example where it's a dead short there, and then I got a quarter wavelength. What if this was 1/8 of a wavelength? Yes. Did you all hear her? Then the shift would be 45 to here, right? Then -1 appears, then another 45 or minus 90-degree phase shift with a minus in front of it, right? Y'all with me? Now, do you feel you can handle that one? How many? Of course not. We don't feel we can handle anything. You can. Now, I mean, do you follow me on this, class? I'm going to ask you something like this on Friday. All right? Here's one other thing I'm going to ask you. What happens if that's not a short right there? Let me take that off.
It is.
Let's make the characteristic impedance on both of these equal to 100 ohms. Suppose I make that 50 ohms and make this lambda over 4 again. Now, how are you going to do that? I want you to just think about this while I'm here, because I know if I don't force you to think about it, you won't. How do I do that problem?
Find the reflection coefficient of the load.
That's the key thing right here. What is it?
50 minus 100 over 150.
50 minus 100 over 50 plus 100, or it's minus 50 over 150, or minus 1/3. Y'all follow me on that? Now, when you track, you would start by saying, I know this is V2 minus. It goes a quarter wavelength. I want to make sure you see this. You understand my reasoning, right? I'm going to do at least the reasoning part of it. I'm going through this methodically and trying to reason out what happens. Well, V2 minus comes out of there. It goes a quarter wavelength. So just before it hits right there, I have V2 minus e to the minus j, and I made it 90 degrees with quarter wavelength, right? Now it hits. So when it hits, the reflection coefficient is minus 1/3, right? Y'all with me on how I'm doing this, please? Please watch. Now that has got to go another quarter wavelength, right? So that means I take e to the minus j90. That's how you take care of phase. You just keep multiplying by e to the minus j, either in radians or in degrees. That's the phase change. And you're always losing phase as you're going, it becomes negative as you're moving through something. Now, when it gets back, now it's here, and that is V2 V2 plus, is it not, class? So now I have V2 minus in terms of V2 plus. One thing I want to make known, e to the minus j90 times e to the minus j90 is e to the minus j180, right? Which is e to the minus j180 is minus 1 with a minus sign. You get rid of all this. And now I have V2 plus in terms of V2 minus, and I can go through that same reasoning process to get the reflection coefficient. Now this is something that I speak of because this type of thing happens. When you're actually when you're building networks, one of the things you do is make sure if you put a short there, the reflection coefficient measured is correct. I'm going to be just honest with you. There's a lot of preventative things you do before you assemble a whole network and realize something isn't working. You try to go through it stage by stage to make sure it works. And knowing the S parameter, I mean, the reflection coefficient is easy to measure, so that's one of the things you do. Okay. All right, burn time. The 4-port stuff is not that important. I wanted to go through that example with you because that particular example is nerve-wracking to people. I'm going to ask you to please do the homework. There will be a quiz at the end of class Friday, and it will be the one that replaces the missed quiz grade for your lowest grade if you missed it. Okay? All right.